All right, let's dive in. Gravitational waves. That's our target today. Ready to get our minds blown.
You bet. And judging from the stuff you dug up, we're going deep, not just skimming the surface.
Yeah, we're going all in. We've got, well, this possible link between gravitational waves and dark matter. That invisible stuff that's like most of the universe's mass.
Right. And then we'll get to this amazing new telescope they're building it to catch even more of these cosmic ripples.
It's wild, right? Like we're solving two huge cosmic puzzles, and maybe gravitational waves are the key. Okay, quick recap for anyone new to the show. What are gravitational waves again?
Okay, so picture a pebble dropped in a pond. See those ripples spreading? Gravitational waves are like that, but instead of water, it's space-time rippling, the actual fabric of the universe.
And these ripples they're caused by the most insane events in the universe, right?
Yeah, like black holes smashing together, neutron stars merging. These events are so powerful, they shake the universe, literally, sending out waves at the speed of light.
Okay, cool. So basics down, now the fun stuff. There's research from UC Riverside suggesting a link between dark matter and these waves. It's like two mysteries might be connected.
Right, and it all comes down to, have you heard of scalar fields? They're kind of like the Higgs boson, but way, way lighter. I'm talking a millionth, even a billionth, the mass of an electron.
Hold on, so these things are so small they make an electron look huge.
Exactly. And this research says these ultralight scalar fields could be the source of both dark matter and the gravitational waves we might detect.
Okay, yeah, my mind is already stretching. But hang on, if these particles are that tiny, how could they make waves strong enough for us to even find?
Well, that's where it gets really interesting. See, these waves wouldn't be from like recent black hole collisions. We're talking about waves from, get this, fractions of a second after the Big Bang.
Wait, are you saying signals from the very beginning of the universe?
Yeah.
That's crazy.
It is. And here's the even crazier part. There's this specific time just after the Big Bang when the universe was expanding at a certain speed. And that let these tiny scalar fields make detectable gravitational waves. It's like they left an echo from that very first moment, an echo we might hear today.
Hold up. Signals from the Big Bang, how could they still be around? Wouldn't they have, disappeared billions of years ago?
That's the thing about these ultralight scalar fields. They interact with the universe in a way that their gravitational waves, they stick around across huge distances in time. Like they've been rippling through the universe for billions of years, carrying info about the very first moments.
That's amazing.
Yeah.
But how do we even try to catch these, ancient whispers from the Big Bang?
There are a few ways. Remember those pulsar timing arrays, super sensitive to the low frequency waves these scalar fields would made? And recent data, well, there are some odd things in there, things that could be explained by these early gravitational waves.
So we might have already seen a glimpse of signals from the start of the universe.
Wow. We might have. It's early, though. Need more data, more study to be sure. But the possibility is, well, it's pretty exciting.
Okay, so we've got these possible echoes from the Big Bang and this incredible new telescope they're making to catch even more waves. Can we talk about that now?
Let's do it. Get ready for LASA, the Laser Interferometer Space Antenna.
That sounds serious.
It is. LASA is it'll change the game for gravitational wave astronomy. Okay, picture this. 3 spacecraft, 1 million miles apart, making a giant triangle in space, using lasers to measure tiny, tiny changes in distance, all caused by passing gravitational waves.
1 million miles, it's far. How tiny are we talking here?
Trillionths of a meter, smaller than the width of an atom.
It's like the most sensitive ruler in the universe. So is this LISA thing real or just an idea?
Oh, they're building it. NASA just showed off a full-scale prototype, the telescopes that will be on LISA. Seeing this tech come to life is something else.
Wow, that's incredible. Tell me, what makes this prototype so special?
Well, first, the main mirror is coated in gold, not just for looks. The gold reflects the lasers perfectly and reduces heat loss.
So a super precise space mirror made of gold to catch these tiny ripples in space-time. Awesome.
It is, and the whole thing is built from this special glass ceramic, Zero-Dur. It's super stable, barely changes shape, even with the crazy temperature swings out in space.
This sounds like sci-fi.
Yeah.
When is this amazing thing launching?
We'll have to wait a bit. LISA is set to launch in the mid-2030s, but the excitement is building for sure.
I bet. So we've talked tiny particles, these scalar fields to the vastness of space, all linked by these invisible ripples, the gravitational waves. Mind-blowing.
And what's even crazier is this is just the start. We're at the beginning of discovering what these waves can tell us. Who knows what other secrets they hold?
It's like we're about to understand the universe in a whole new way. So where do we go from here? How else are gravitational waves created? What can we learn from them? I guess that's for part 2 of this deep dive.
Right, so those potential gravitational wave echoes from the Big Bang, well, they're not the only ripples out there. There's a whole spectrum of them from all kinds of cosmic events.
Besides those super early waves from the scalar fields, what else is like shaking up space-time?
Well, think about it. Anything with mass that's accelerating creates gravitational waves. But to detect them here on Earth, we need something really massive and accelerating a lot.
So me, like, running for the bus wouldn't be enough.
Probably not, though technically you are making tiny, tiny gravitational waves. We're talking like black holes merging, neutron stars spiraling into each other. Those are the cosmic heavyweights, making waves strong enough for us to pick up.
Yeah, I can see how those would be intense. But if they're so powerful, why are the waves so hard to actually detect?
Good question. It comes down to distance. Imagine shouting to someone across a field. The further they are, the harder it is to hear you. Same with these waves. Events might be super powerful, but happening so far away. By the time the waves get to us, they've spread out, gotten super faint. We're talking distortions smaller than an atom.
Seriously,
Yeah.
that's incredibly tiny. No wonder it took us so long to figure out how to even detect them.
Exactly. It took some serious brain power and precision to build stuff like LEGO, the Laser Interferometer Gravitational Wave Observatory. It's basically a giant, super precise ruler using lasers and mirrors to measure these tiny distance changes, all caused by passing gravitational waves.
So like a cosmic seismograph, picking up tremors from these far-off events.
Great analogy. And thanks to LIGO and other detectors like it, we've found some amazing things.
Thank you.
Observed black hole mergers, neutron star collisions. We're even starting to piece together a kind of cosmic family tree, going back billions of years.
That's so cool. So what kind of info can we actually get from these waves? What secrets of the universe can they tell us?
Well, for one, there's strong proof for Einstein's theory of general relativity. His predictions about gravity in extreme places have been confirmed by these observations.
Einstein was right again? Shocker. But, like, beyond proving him right, what else can we learn?
We've learned about how stars live and die, how black holes form, what matter is like under extreme pressure. We're even starting to use gravitational waves to study dark matter and dark energy. You know, those mysterious forces controlling the universe.
It's like we've got a whole new sense, a way of seeing the universe that was totally hidden before.
Exactly. And this is just the start. As our tech gets even better with projects like LISA coming, who knows what else we'll find.
I'm on the edge of my seat already.
Yeah.
Speaking of LISA, we talked about its size and how sensitive it is. Can we dig deeper into what makes it special and the kind of science it'll do?
Of course. It'll open up a whole new world of gravitational wave astronomy. It's going to be 1,000,000 times larger than the LEGO, stretching across millions of miles of space, meaning it'll detect much fainter waves and ones with lower frequencies.
It's bigger and more sensitive, I get it. But what does that mean for the science? What can LISA see that LEGO can't?
Well, for one, it can detect mergers of supermassive black holes. Those are the giants at the centers of galaxies, millions, even billions of times the mass of our sun.
No way. So we'll be able to, like, watch these cosmic titans clash, warping space-time on a galactic scale.
Exactly. And not just watch, we can study those mergers in detail, learning how galaxies evolve, how these huge black holes shape everything around them.
It's like we're going from studying individual stars to watching entire galaxies evolve.
And there's more. Because LISA can pick up lower frequency waves, it can also detect events from much earlier in the universe. We might even be able to detect the gravitational waves from cosmic inflation, that rapid expansion just after the Big Bang.
Wow, that would be amazing. Like listening to the first heartbeat of the universe. Okay, I'm totally sold on LISA. I can't wait for it to launch. But until then, any other projects or tech coming up that are pushing the limits of what we know?
There are. Those pulsar timing arrays we mentioned. They're getting even more advanced, sensitive to even lower frequency waves than LISA, meaning they could potentially detect those supermassive black hole mergers from the very early universe, billions of years ago.
Wow, that's incredible. It's amazing how scientists are finding all these different ways to detect and study gravitational waves. So, with all these projects and discoveries, what's next for this field? Where are we headed in our quest to understand these cosmic messengers?
The future for gravitational wave astronomy, it's super bright. With LISA and those pulsar timing arrays, it'll be like a whole new view of the universe across huge distances and time.
Sounds like we're entering a golden age of discovery. What are some of the big questions we might answer in the next, I don't know, 10, 20 years?
So many. We might finally figure out dark matter, dark energy, see the first stars and galaxies form after the Big Bang. We might even detect the waves from the Big Bang itself, the very first moments of creation.
Wow. Those are some seriously huge questions. And we're talking about using these invisible ripples in space-time to find the answers. It's just mind-blowing.
It is. And it's not just looking back in time either. Gravitational waves, they could totally change how we understand physics itself. We could test different theories of gravity, search for new particles, even explore what space-time actually is.
So it's not just astronomy, cosmology. It's like pushing the boundaries of physics as a whole.
Exactly. Gravitational wave astronomy, it brings everyone together. Physicists, astronomers, engineers, computer scientists, everyone working to unlock these secrets of the universe.
The ultimate science team up. So for someone just learning about all this, what's the one thing you'd want them to remember?
I think the most important thing is this is a brand new field. We're at the very beginning of an incredible journey. Every new detection, every observation brings us closer to understanding the universe in ways we never thought possible.
It's like we're opening a whole new chapter in the story of the cosmos. And we're all writing it together, one gravitational wave at a time.
That's a great way to put it. And who knows what we'll find in the next chapters, right?
I can't wait to see. Thanks for taking us on this amazing deep dive. My mind is officially stretched.
My pleasure. And to everyone listening, keep looking up, keep exploring, keep asking those big questions, because the universe, it's full of amazing things just waiting to be discovered.